In this video, we are going to learn how to use the Taylor series for three very common functions, e to the x, sine of x, and cosine of x, to develop the Taylor series for more complicated functions such as e to the 5x, or sine of x squared, or sine of x cubed, or even others that are more complicated. And so we want to start by talking about the difference between a Taylor polynomial and a Taylor series. So let's get started. We want to find the Taylor series for f of x equals e to the 5x centered at c equals 2. So this is not a Mclaren series because that would be one centered at c equals 0. We want to give the first four non-zero terms, and then the new thing that we see in this video is they are asking you for something called the general term, which we're going to talk about in just a moment. So let's just start writing some derivatives down. We have our original function e to the 5x. And then we have our first derivative, which is going to be by the chain rule, 5e to the 5x. And then the second derivative, chain rule again, 25e to the 5x. Third derivative is going to be 125e to the 5x. And because they're asking for the first four non-zero terms, this should be all we need to do. And now we're going to plug in our center. So f of 2 is e to the 10th, and f prime of 2 is going to be 5e to the 10th, and f double prime of 2 is going to be 25e to the 10th, and f triple prime of 2 is going to be 125e to the 10th. So normally, if they were asking you for a Taylor polynomial of fourth degree, or let's say in this case it'd be a third degree, we would say p of 3 of x equals, and we would list only the first four terms, which would get us to the x to the third term, and that would be an approximation of e to the 5x. However, the difference here is they are asking us for a Taylor series, and so a Taylor series means we want to list all the terms out. So that means we are going to say f of x is equal to the first term. We're going to use this Taylor series expansion. So f of 2 is e to the 10th. And then we have f prime of 2, which is 5e to the 10th. And that's going to be centered at 2, so x minus 2. And I'll put that to the first power. And then we have 25e to the 10th, x minus 2 squared over 2 factorial. And then we have 125 e to the 10th x minus 2 to the third over 3 factorial. And then they want us to give a general term. So a general term is nothing more than a term that will work for any value of n. And so we will say plus dot dot dot, which means this list will continue forever. And we will sum up from n equals 0 to infinity. Now let's just take a look and see what we have here. Well, if I put a 1 right here, we have powers of 5. 5 to the 0 is 1, 5 to the first is 5, 5 squared is 25, 5 cubed is 125. So we are going to need something in our general term that it represents the powers of n. So we'll say 5 to the n. And then we will need an e to the 10th power is common on every term, so we'll put that in there, e to the 10th. And then our x minus 2 is common to every term, but x minus 2 is raised to some power. So we'll say x minus 2 to the nth. And then the power that it's raised to is the same factorial that's below, so we'll call that n factorial. Now, if you are very confident about your work, then you can pretty much go on from here. But if you're not sure at the beginning, it's always best to check it by plugging in your first couple values of n, and make sure that you're getting these first few terms of your Taylor series expansion. Now there are three special Maclaurin series that you absolutely must have memorized for the AP exam, and they are sine of x, cosine of x, e to the x. And you can take some time on your own to generate these. Here are the first few terms of them, and also their general term as well. And so you can take some time to generate these on your own, but for the purposes of this video, I am going to assume that you have these already memorized, because we are going to take these three and we are going to manipulate them over the next couple of videos. We're going to manipulate them to find other Taylor series for more complicated functions by using the following techniques: substituting into the series, multiply or dividing the series by a constant and or a variable, adding or subtracting two series together, or differentiating or integrating a series, or recognizing it as a sum of a geometric power series. None of these probably make any sense to you, so let's just jump in with an example. Here they are asking us to find a Maclaurin series for f of x equals sine of x squared. Find the first four non-zero terms and the general term. So we've already got written out up here sine of x. So what we need to do is we need to take this x squared and we need to actually substitute it in for all these x's, and also we need to take it and substitute it into the general term for that x, so that we don't have to think about what the general term will be. We already have the general term by substituting in. So let's go ahead and do that. Sine of x squared is simply going to be, we're going to replace this x with x squared, and then we're going to replace this x with x squared, which you have to be careful, that's going to be x squared cubed, and that's going to end up giving us x to the 6th. We'll expand that in just a second. So 3 factorial, and then plus x squared to the 5th over 5 factorial. And they want the first four terms, so we'll do one more. X squared instead of x to the 7th over 7 factorial plus dot dot dot. The general term is going to be the summation from n equals 0 to infinity. And we need something that's going to make it alternate, so that's the -1 to the n. And now we're going to replace the x with x squared. And in the general term for sine of x, the x is already raised to 2n plus 1. So we need that 2n plus 1, which, by the way, is the expression for odd numbers. So we also need that same expression on the bottom to capture the factorials as well. So we can write this out in simplified form as x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial. And then our general term is simply going to be the summation from n equals 0 to infinity, -1 to the n. And when we have a power to a power, we multiply those powers. So that's going to give us x to the, you have to distribute the 2 into both of those. So that's going to be 4n. Let me write it 4 a little bit better here. 4n plus 2. And all of that is over 2n plus 1 factorial. All right, in this third example, it says find a Maclaurin series for f of x equals x times cosine of x. So this is a pretty simple one. All we need to do is we need to take our Maclaurin series for cosine of x and simply multiply it by x. So we're going to take each term and multiply it by x. So maybe we will put this like this, and we can see that we just need to distribute the x in there. So that's going to give us x minus x cubed over 2 factorial plus x to the 5th over 4 factorial. And then we need the next term, which is going to be minus x to the 7th over 6 factorial and plus dot dot dot. And we're going to actually take our general term as well, and we're going to multiply that by x also. So that's going to be n equals 0 to infinity, and we need a -1 to the n to make it alternate. And when we multiply this x to the first right here times x to the 2n, the bases are the same, so you add the exponents. So that's going to be x to the 2n plus 1 over 2n factorial. Those are the first four terms, and this is the general term for x cosine x. Okay, now we have a more complicated series, and it is the Series h of x is equal to e to the x plus e to the negative x divided by 2. So perhaps I'll write this as 1/2 times e to the x plus e to the negative x, and that'll hopefully help us see what we need to do. We need to take e to the x, our Mclaren series for e to the x, which is right here, and then we need to add to that e to the negative x, and so we need to figure out how we can write e to the negative x. Well, that's just going to be a substitution. That's going to be a substitution. So we can take negative x and we can substitute it. Actually, we don't need to substitute it into the general term. We can substitute it into all of these places for x into e to the x, and we will get a new Maclaurin series for e to the negative x. Add those two together and then multiply your answer by 1/2 and then write the general term from there. So let's go ahead and do that. E to the x we can write as 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And those are the first 4 terms. And e to the negative x simply means to go in and replace these x's with negative x. So that's going to be 1. This x is going to turn into negative x plus, now negative x squared is going to still keep it positive. So we'll write that there. But if you have a negative number to an odd power, that's going to make it negative. So the next term is going to be negative x cubed over 3 factorial. And if we add these together, we will notice that the x and the negative x cancel, the x cubed and the negative x cubed cancel, and if we add the terms that are left together, we get 2, and then maybe it'll help us if we put this as a 1 and a 1. The common denominator is 2 factorial, so all we need to do is add up the numerators. So 1x squared plus 1x squared is 2x squared, and we keep the common denominator. But we only get 2 terms, and they want 4 non-zero terms. So that means we need to continue our list, and we need to make this x to the 4th over 4 factorial, and then x to the 5 over 5 factorial. And then this will be x to the 4th over 4 factorial, and then minus x to the 5th over 5 factorial. That should be enough for us to see the pattern. The next term is going to be plus 2x to the 4th over 4 factorial. And the x to the 5ths are going to cancel. And then we have our x to the 6th are going to add together. So that's going to give us 2x to the 6th over 6 factorial. Now don't forget we need to multiply this by 1/2. When we do that, basically all these 2's in the numerator just go away. And that's going to give us 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial plus x to the 6th over 6 factorial plus ... So this kind of looks like the cosine Maclaurin series, except it's not alternating. You have even powers over even factorials. So we can write this simply as the cosine function, except without the alternating part. So that's going to be x to the 2n over 2n factorial. All right, next example says give the first 4 non-zero terms of e to the x. Well, that's pretty simple. We've done that before, and that is simply going to be e to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And there's our first 4 terms, and the general term is simply n equals 0 to infinity of x to the n over n factorial. Now it wants us to use our answer from part A to find the limit as x approaches 0 of f of x minus 1 over 2x. So here I'm going to essentially say there are 2 different ways to do this particular problem. One is very fast and the other takes a little bit more time. If you recognize this to be a L'Hopital's rule problem, it's very quick. Because when you plug in 0, matter of fact, let's write f of x. Since we know f of x is e to the x, let's just rewrite this as e to the x minus 1 over 2x. If we plug in 0, e to the 0 is 1, minus 1 is 0, and we plug in 0 to the bottom, we get 0. So the first is the L'Hopital's rule approach. And so all we'll do is simply take the derivative of the top, which is e to the x, and the derivative of the bottom, which is 2. And then we're going to plug in our limit. So we will take the limit as x approaches 0, and we will get 1/2. And we are done that fast. However, let's say we come across a problem like this, and it is not a L'Hopital's rule problem. It doesn't give you 0 over 0. Well, for this, we need to take our first 4 terms of our e to the x and subtract 1 from that. So let's take 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and take all of that, subtract 1 from it, and divide it by 2x. When we subtract 1, that's going to cause these two to go away, and then we're left with x plus x squared over 2 factorial plus x cubed over 3 factorial, and the limit as x approaches 0. And we need to divide that by 2x. When we divide that by 2x, we're going to take 2x and we're going to divide it into each term on the top. When we do that, the first term is simply going to be 1/2, plus the other terms are going to have x's in them, so it will be x over 2 times 2 factorial plus some other terms that have x. And when you plug in 0 into all those remaining terms, they will all go away, and what you'll be left with is the first term, which is 1/2. All right, in this last example, you will finally see the great value in learning and using the Taylor series idea. So we're going to start with, it says use your answer to part A. Now part A basically just said develop or write down the first 4 terms of cosine of x, which we have before us right here, at least the first 3, and we have the general term. Now it says use those 4 terms to develop a Maclaurin series for 1 minus cosine of x over x squared. So we're going to take the first 4 terms of our cosine series and we're going to do 1 minus those. So we will write 1 minus parentheses the first 4 terms of the cosine series. So that's going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And we're going to take that and we're going to divide that by x squared. When we do that, the 1's are going to cancel, and then all the signs inside of here are going to change because we have to distribute a negative to each term inside the parentheses. So that's going to give us a positive x squared over 2 factorial, and then a minus x to the 4th over 4 factorial, and then a positive x to the 6th over 6 factorial, and divide that by x squared. So once again, similar to the last problem, we're going to take this x squared and we're going to divide it into all 3 parts on all 3 terms on the numerator. When we do that, we're going to end up getting 1 over 2 factorial, which is just 1 over 2, minus x squared over 4 factorial, and then an x to the 4th over 6 factorial. And this is our, actually we need one more term, so that's going to be minus x to the 6th over 8 factorial. And the general term is going to be, let's just see what it would be, plus dot dot dot, summation from n equals 0 to infinity. And we will have, first of all, something that makes it alternate, negative 1 to the n. And we will need an x to the 2n. And then we need the factorial to be 2 bigger than the power. So that's going to be 2n plus 2 factorial. Okay, part C is where it all comes together. It says use your answer to part B to approximate the value of the integral from 0 to 1 of 1 minus cosine of t over t squared dt so that your error in your approximation is less than a certain number, 1 over 500. Now, just keep the big picture as far as what we've been doing in mind here. We have written a polynomial that closely approximates this function. Here is the value in that. Let's say we have a function like 1 minus cosine of t over t squared that we absolutely cannot integrate by hand, but we would like to figure out what the value of the integral is from 0 to 1. But it is not something that we can integrate by hand. But guess what? We can use the Taylor series, because now we can replace this function that we cannot integrate by hand with a polynomial that we can integrate by hand, and you're going to see how close our approximation is to the actual integral. So let's go ahead and integrate this from 0 to 1, and we're going to integrate not the function that we can't integrate, but we're going to integrate this function here, which is our approximation of it. And, oops, we need this to be minus x to the 6th over 8 factorial, and dx, letters really don't matter. So 1 to 0, it's going to be 1/2 x minus x cubed over 3 times the 4 factorial, plus x to the 5th over 5 times 6 factorial, minus x to the 7th over 7 times 8 factorial. And then now we're going to plug in our upper and lower limit. So we plug in our upper limit, and that just simply is going to give us 1/2 minus 1 over 3 times 4 factorial plus 1 over 5 times 6 factorial, and that should be enough. Now, we recognize this to be an alternating series. That's the key to this problem. It's an alternating series. How do we know? Because the 3 conditions apply. Number 1, these terms are alternating. Plus, minus, plus, minus. Second, the limit as n approaches infinity of this expression is going to 0. And 3, it's a decreasing function. So therefore, we can use the alternating series remainder to approximate this series. So now we can say we want it to be less than 1 over 500. So that means we need to find the first term that is less than 1 over 500, and that is our neglected term, and then sum up the other terms before that. So if we write this out, maybe I'll continue it up here. So we have 1/2 minus 1 over 72, which is what you get when you do 4 factorial, which is 4 times 3 times 2 times 1, which is 24 times 3. And then we get 1 over 3600. Now 3600 is clearly smaller than 1 over 500. So this term here is our first neglected term. So that means we only need to add up 1/2 minus 1 over 72. And that's going to be 36 over 72 when we get a common denominator, minus 1 over 72. And so our integral is 35 over 72. Now let's just see how close our approximation of this integral is to the real integral. So when we use our Taylor series, 1/2 minus x squared over 4 factorial plus x to the 4th over 6 factorial, and we approximated that integral to be 35 over 72, as a decimal, that is 0.486111. If you type into your calculator in radian mode 0 to 1 of the actual function 1 minus cosine x over x squared dx, you will get 0.486385. Hey, you got to admit, that's pretty cool. Our approximation by Taylor series by hand is extremely close to the real one. As a matter of fact, the actual value minus our Taylor series approximation is close to within 3 decimal places, 0.000274.